Okay, hello everybody. My name is Frank Würthwein, and I'm the director of the San Diego Supercomputer Center. And I'm here to talk to you about reasons for composable systems. There is two types of reasons, and I will spend one slide each to talk about them. The first one is that the social organization of computing requires us to work within different environments on different platforms, and we would ideally want to use the same hardware and make that same hardware available to as many modalities of use as possible, where modalities of use are dictated to us by the kinds of social organizations that we're working with. I'm giving examples. Traditional HPC is most commonly accessed via a batch system. And in our case, that's Slurm. The entire universe of containers is typically accessed via Kubernetes. And so there is software composability for science workflows and services and et cetera, et cetera, et cetera. It's an entire universe in its own right. And that has its own interfaces and the way it presents itself to the community. And third, there is bare metal types of interfaces via testbeds like Chameleon, Cloud Lab, and Fabric. And the user communities that want to have access to hardware via those want to see them in some form or fashion of bare metal. And we would ideally want to use the same hardware, make it available to all three of them. And in the past, we developed things of this sort by ourselves. And for the future, we have now selected Bright Autoscaler technology for both expanse and NRP systems at SDSC to do exactly this. Apart from the social organization of computing, there is another issue that lends us or moves us in that direction, and that is hardware diversification. The market today offers us a dazzling set of hardware choices to compose into host systems. There is multiple different Xilinx Alveo cards. There are different Ampere-level NVIDIA GPUs, not counting a myriad of older cards that are around, or gaming cards, RDXs, you name it, AMD, Intel GPUs. There is the concept of DPUs from various vendors that range from smart NICs to GPUs on NICs to FPGAs on NICs. There's a variety of different CPU host systems. There's different amounts of NVMe added to hosts, et cetera, et cetera, et cetera. And in an ideal world, we would be able to compose systems out of devices ad hoc in an automated computer-controlled fashion via some sort of API, and do all of this dynamically, and voila, off we go. We provide the same hardware in different ways, different configurations to different people at different times. And all of this we will actually have deployed in, we will deploy something called the NRP system. It will be deployed in 2022, and we will explore implementing these capabilities via GigaIO. GigaIO is the core thing that will allow us to do this.
Thanks, Frank. This is Matt Demas from GigaIO. I am the CTO of Global Sales. Before we kind of get into this, I want to give you a quick little synopsis of what composing with GigaIO is really all about. So I'm going to give you a quick little introduction, and then I'm going to go hand it over to Martijn. He's going to talk about the Bright integration with GigaIO. But so you have some context, I'm going to give you a real quick intro. All right, so to this point, you'll see composability, and everybody talks about composing storage. So your Dell, your HP, and others, they're all composing storage. Well, with GigaIO FabreX, we've actually had a way to now compose not just storage, but network devices, accelerators, CPUs, and now even the memory. So in application-aware environments, we can compose memory. We can also now drive towards a CXL environment where we're able to go and have full cache coherent memory composability also. That's coming out here in the near future as CXL enters the marketplace. Now, we have two different types of composition. One is simple composition, meaning that I am going to create connections between devices and servers. Those devices will then be physically mounted to those servers, and that server will now see those devices as if they were local inside that system. So thinking about, I have a bare metal system that today has a very small amount of resource in it, but I can use software and actually give that server more resources to do the job that it needs. The other type of composition that GigaIO supports is called extended composition. And what this means is we have multiple servers or nodes, as I want to call them, intercommunicating to themselves. And that's all happens across memory. Why this is important is we can enable certain communication protocols like NVIDIA over FabreX or GPU Direct RDMA, libfabric, even run MPI jobs across that low latency interconnect. But it also lets us lets any server go and view and work with the resources in another server. So I can actually communicate directly to a GPU in the server sitting next to me or in the rack next to me, and give ultra low latency, ultra high bandwidth inter-node and inter-device communication, really enhancing the capabilities of AI and HPC. Some of the benefits of composability is going to be really faster time to insight. So because of this unique capability to provide whatever resources I want to have in that box to go run a specific job, I'm able to go maximize my efficiency of those devices, but also make sure I have the right devices for that exact job. And this can really help improve the time to insight, whatever that insight is to you as an end customer. So that insight could be, I want to be able to get to a solution to go make money faster. It could be, I want to be able to go come out with a new product quicker. It could be, I just have some new science I'm trying to do in a university standpoint, and I want to be able to go support as many customers as I can in the most efficient way possible. Now, the next side is better business agility. So this comes more down to when I have a large system that I'm trying to support a lot of users in, I don't have to just rip and replace that whole system because it was a tightly integrated package. Because I've now put myself in a scenario where I'm composing, I can replace CPUs separately from GPUs, separately from network, separately from storage, and really help my business make sure I have the right capability at the right time. And then this drives into sustainability. So when I can also replace things at separate times, I'm able to go do more with less hardware. I'm able to really help as we're trying to go reduce carbon emissions and lower power utilization across our planet. So here's a real quick diagram of kind of how our memory fabric works. You'll see here on the left side, you have 3 servers, and then on the right side, you have a whole bunch of resources. So traditionally, those resources lived inside the servers. Well, in our composed environment, they're actually living in these resource chassis. And those resource chassis connect into our memory ring. And then from there, those servers can access those GPUs directly across that memory ring. So when you think about today, you're using terms like RDMA, we're not actually using RDMA, we're using true DMA or direct memory access. So we're not having to go translate protocols and that type of thing to go intercommunicate between nodes or intercommunicate between devices. All of that happens natively as a direct memory access. And last, you see at the bottom is our shared memory appliance. This is going to be a system full of memory that every node and every device has access to. So I can use that memory to either expand my existing server memory within the server, or I can use it even like a NAS where I have multiple servers accessing the same DRAM simultaneously for ultra high speed, low latency memory access. And as you can see here, this works not only great for node to device. If I'm talking to a GPU or I'm trying to go say pair 32 GPUs to a server, it also works really well node to node. When I'm running my MPI workloads, I can run them across that same DMA-based network. And I can also do device to device where I can allow my GPUs to talk to each other, whether they live in the same box or whether they live in different boxes. Here's an example of how the traditional RDMA setup works. Today, when I'm going to run DGXs, I actually am going to have to say this, the bottom left-hand corner of my primary node. To go communicate to the GPUs and the other nodes, I have to go through the host memory, the IOMMU, and then PCI translation to go enter an RDMA network. From that point, I can go communicate across that RDMA, and I would go to the next host. I have to then go back through PCI translation, back to the host bridge, back through system memory, into the kernel in order to be able to access those GPUs inside that box. That's a very long, lengthy, high latency process that really impacts the overall performance of what a multi-node system can do inside AI and HPC workloads. So with GigaIO, we eliminate a lot of those bounce buffers. You'll see that that same primary node now just has to communicate through host memory, then the IOMMU, and then it actually has direct access into the GPUs of the other nodes. We're completely bypassing the system kernel. We're bypassing every other translation that may have to happen in that system. We're talking directly memory to memory from GPU and that primary node to the GPUs of the additional nodes to really help reduce reduce the amount of latency, but also really increase that time to value. GigaIO FabreX was designed from the beginning to be an open architecture. So we created this with the idea that everybody can go ahead and write their applications in. In fact, we did it in such a way we don't even have our own GUI. We wanted to make sure that whatever tools you're using today are the same tools you're going to use tomorrow. So FabreX is meant to kind of be that invisible layer underneath that just makes things work and improves efficiency without having to completely change the way operations are done. So that's why we included things like all these different host services. So you're using the same types of services you're using today, but we just give you another transport protocol to run across. We added drivers to give you that ability to automatically allow those tools to work across that new fabric without having to re-architect everything. You'll see that we work with in containerized environments, VMs, big data, deep learning, it doesn't really matter. Whatever you're operating today, it still continues to work. And then we have lots of different hardware providers, right? So AMD, Intel, we work on Dell servers, we work on Supermicro servers. We also even work with ARM servers now. When we'll work with really anything that fits into an add-in card or UDAT2 slot. So if I want to go use NEC vector engines or AMD GPUs or Intel GPUs or one of the 204 stealth mode accelerators out there, they all work inside of our environment. So we've completely designed it to allow companies to be flexible, versatile, and really kind of embrace the next generation of AI has to offer. And then lastly, kind of the most important piece in this is that we have made it very open from a composition software perspective. So you'll see companies like Bright that we're going to talk to next. They're able to go integrate right into this, right into GigaIO, and they're able to kind of take that power that GigaIO brings, bring it into their software platform, and let it really act as an on-prem cloud. So so here we are, the values of GigaIO for HPC are the HPC clusters now can support many, many functions, right? In the past, you've seen clusters that were very static, very hard-coded, and they could do a lot of different things, but you had to change your software to go fit that cluster. Well, now in a composed environment, I can truly have software-defined hardware where my hardware will change to meet my software needs. And I can really go solve whatever problem I want to solve without having to go make it work for that type of system. Systems can be upgraded. They don't have to be completely replaced. We talked about the sustainability aspects. And then I'm able to take advantage of new technology. So how many new GPUs have come out over the last 3 years? And you may be sitting there with servers that are 3 years old and go, those servers can't support these new GPUs. They weren't certified for them. So I have to wait till I go replace my server hardware in order to get these new accelerators. Well, not with composability. Now, because we've disaggregated all those resources, I can go replace or add to just accelerators as I need them, or allow researchers to bring their own accelerator to your environment. We also allow us to isolate sensitive workloads. So this goes to the MPI aspects of what operates across fabrics. And that means that I can choose, hey, this workload I'm going to run across my InfiniBand environment. This workload, I want to move it to the fabrics environment, so I have more bandwidth, lower latency, and I'm closer to my GPUs. I can pick and choose based on the workload exactly how that operates. Again, true software-defined hardware. And lastly, the ability to integrate into these great tools like Bright. Now with that, I'm going to actually go hand this over to Martijn, and he's going to talk to you about the Bright integration into GigaIO.
So in case any of you is not familiar with Bright Cluster Manager, let me give a brief introduction. So Bright basically allows system administrators to turn a pile of hardware into a fully functional HPC cluster. We can go from a situation where we have a bunch of servers that have nothing installed onto them to a cluster that is completely ready for production. So in addition to streamlining cluster deployments, Bright also allows clusters to be managed, monitored, and health checked after they've been deployed. So we integrate with Kubernetes, with Ceph, several HPC job schedulers, and also with Jupyter in order to provide an infrastructure that can be used from web browsers. So at the heart of Bright, there is a cluster management daemon that's running on all the nodes inside of a cluster. And these cluster management daemons are interacting with each other in order to make the cluster manageable. The cluster management daemon that's running on the head node of the cluster exposes an API to the outside world that external applications can talk to. One of those applications is BrightView, which allows system administrators to manage a cluster from their web browser. For those administrators who prefer to work from the command line, there is Cluster Management Shell, otherwise known as CMSH. And lastly, it is also possible to interact with the API directly by using Python, using our Python bindings or our C++ binding. And it's also possible to interact with the cluster from Ansible by taking advantage of the Ansible module collection that we've recently made available. It is possible to spin up Bright clusters on-prem, in the cloud, in hybrid scenarios where part of your cluster is on-prem and it is extending into the cloud. And it's also possible to create cluster setups that span different geographical locations by creating edge setups. Okay. It's very easy to repurpose nodes on the fly. So a node that is running Slurm could be turned into a Kubernetes node within seconds. And that can be done either manually by the administrator, but it can also be done based on the workload that is running on the cluster. Lastly, Bright provides a rich collection of HPC and machine learning tools and libraries to make it as easy as possible for end users to spin up their workload on the cluster. So what I'd like to talk about today is the work that we've been doing for Bright 9.2 involving GigaIO integration. So Bright 9.2 is currently in its final QA phases, and we expect it to be ready for release by Q1 of 2022. So what we've done is we allow for PCIe devices to be pooled and assigned to nodes in the cluster using the Bright management interface. So instead of having to interact directly with the GigaIO API that the switches provide, you can do all of this from inside of Bright's management utilities using BrightView or CMSH, or perhaps by interacting with the Bright API. So Bright also streamlines the fabric configuration process, so you can be sure that you've wired everything correctly. After you've selected the topology that you want to use in your fabric, Bright allows for composition and decomposition of nodes to resources. So those compositions can be done manually by the system administrator. So this is the functionality that we will be releasing immediately with the release of Bright 9.2. But in the future, we also plan to make it possible to have bindings take place automatically based on job requirements that the users are submitting to the workload management system. So GigaIO FabreX switches and resource boxes exist as devices in Bright's infrastructure, and therefore they can be monitored and health checked. So you can be pulling metrics from your FabreX switches and from your resource boxes, and they will show up as metrics in Bright's monitoring infrastructure. So this is what BrightView looks like with the GigaIO integrations. If you select your cluster and you go to the FabreX tab, you can see all of the different fabrics that have been defined on my cluster. If I then select one of these fabrics, I get a number of tabs over here on the right. So we're looking at the settings tab at the moment. And you can see that we've selected a 2S4x4-1 topology, which means 2 switches, 4 nodes, and 4 resource boxes. And 1 is just a serial number because there's multiple of these topologies that exist. So you can think of a topology as basically a template where switches and resource boxes and nodes still have to be filled in. So we apparently have a device, which is a switch, which is called fswitch27, and we have one called fswitch28. And these have been filled in as the switch 1 and switch 2 in this topology template. And if you look closely at switch 1, you'll see that port 1 has been assigned to node 20 and port 5 has been assigned to node 21. And we have 2 resource boxes that are connected on port 9 and port 13. Here we're looking at the bindings tab, and you can see both of these switches being displayed in a graphical way. We're basically using colors in order to show what is connected to what. In this view, we have 4 nodes. 2 of them are connected to fswitch28 and 2 of them are connected to fswitch28. And here we see the resource boxes that are connected to both of those switches. So right now, no bindings have been made yet. So in order to bind a resource box to a node, we just drag and drop the node to the resource box or the resource box to the node. And as you can see, we've made two bindings. So node 20 is now bound to IO 44 and node 21 is bound to IO 45. Here's a different topology. So we're looking at a 2S4x4-3 topology right now. And this is a topology where one switch has all the nodes and the other switch has all the resource boxes. So we've selected F switch 09 as switch 1 and F switch 10 as switch 2 in this topology. And we're looking at the second switch at the moment. And you can see that we've assigned IO 01 through IO 04 to the ports on this switch. Now, if you look in bindings mode, you can see this in more detail. So we have all of the nodes connected on one switch and all of the resource boxes connected on the other switch. Now you also see these so-called cascade links being defined over here. So this switch has 4 cascade links and they end up over here on this switch. So these are basically the connections between these two switches. Now, in order to make a binding between a node and a resource box on the other switch, we first have to bind the node to the cascade link. So we do that by dragging, in this case, node 15 to this cascade link over here. And you can see that on the other switch, it will show up red. Now, in order to bind a resource box to that node, we have to bind the resource box to the cascade link over here on this second switch by dragging and dropping. So in fact, we can do that with multiple resource boxes. So right now we have assigned 4 resource boxes to this node 15. And if you want extra bandwidth, we can also add another cascade link. So here's a different setup. Right now we have 2 resource boxes bound to node 15, and we have bound 2 other resource boxes to node 18. So this is how easy it is to make bindings using BrightView. And the same can be done using CMSH and the API. With the release of Bright 9.2, we're just getting started with composable infrastructure. There's some future work that we're planning to do. So we are planning to provide more insight into what exactly has been plugged into each slot of a resource box. We also want to make it possible to identify miscabling of resources. So there's a lot of cables going from the nodes to the switches and between the switches and from the switches to the resource boxes. So it's easy to make a mistake. And using cable identifiers, it is possible for Bright to identify cables that have not been plugged in properly. We also want to make it possible to make bindings automatically based on the requirements of jobs that users are submitting to the workload management system. So the idea is that when jobs request resources that are not available at the moment, the job will remain unscheduled in the workload management system. So Bright has a component called Bright Autoscaler that can be very useful here. So the current tasks that Bright Autoscaler performs is it identifies jobs that are waiting for resources, and it makes extra resources available so that the jobs can be scheduled. So for example, it can power on extra nodes in the cloud or create extra nodes in the cloud or power on extra local nodes, whatever is necessary to create the resources that the jobs are waiting for. So after the resources have been made available and the jobs run, those resources will become free again. So another task that Bright Autoscaler performs is it identifies resources that are no longer in use after the job's complete, and then it makes those unused resources unavailable again. So for example, in the case of physical nodes, it powers off those nodes, or in the case of cloud nodes, it may either power off those cloud nodes or it may actually terminate those cloud nodes. So in the context of composable infrastructure, we have an enhancement that we want to make to Bright Autoscaler, which is to identify jobs that are waiting for resources that need to be bound to nodes. So for example, a user may be submitting a workload management job that requests 4 GPUs. And at the moment, there may be no nodes that have 4 GPUs available. So what the future Bright Autoscaler will do is it will bind those GPUs dynamically to the nodes. And at that point, the workload management system will pick it up and it will allow the job to be scheduled on the nodes that Bright Autoscaler has made available. After the job runs, the resources will no longer be necessary, and the task for Bright Autoscaler is to identify those unused resources that are currently bound to the nodes and then unbind them so that they can be made available for different jobs that will run on different nodes. So I'm now going to turn over back to Matt, who's going to talk more about GigaIO.
Thank you, Martijn. Appreciate that. Now I'm going to go back and talk to you about a couple of use cases. So these are the most common use cases that we've been seeing composability while being used with HPC and AI. So I'm going to kind of walk you through a few of these and explain to you why it's been such a big impact for these customers. So the first one I'm going to talk to you about is the university use case, right? This use case is near and dear to my heart. I work with universities for a little while now, kind of really focusing on the fact that they have so many schools of business, right? Today, when I talk to them, they're always trying to fight budget constraints where each individual school of business will go get, or even project will go get their own unique funding. And that funding source will come directly to them, and they'll want to be serviced or potentially serviced by central IT. And central IT is going to go, well, I've got this system here that you could try to use. And they're going to go, well, does that work for my use case exactly? Well, if you made this change or that change, it could work. Okay, so the school of business then saying, well, I have to change my research, change what I'm doing to go fit your system. How about if I go buy my own IT? And they'll put their own little small IT system in a closet, in a lab, and it now becomes shadow IT, unmanaged IT, and equipment that may get used for a short period of time and then literally be abandoned. So composability has really enabled central IT to go say yes to all those schools of business. So here you're seeing an example of mechanical engineering or bioinformatics or computer science, and they all have different unique workloads. So instead of now having one big system or even a couple medium-sized systems to go support all these different groups, I now have a cluster, but I have disaggregated resources of all different kinds. I have the ability to go compose memory and storage and even network devices, and I can go create a unique system for whatever their need is. And if it comes down where the bioinformatics guys come in and say, I really want to try this new accelerator, and they say, okay, I need to buy, instead of having to buy a stack of systems, all I have to do is say, I can go buy 4 of those accelerators, put them in my accelerator pool, and let you use my existing compute, my existing network stack, everything else that already is there today, and just simply add an accelerator resource to that pool. And now every system inside that pool has access to that new resource. Now, when the bioinformatics guys are done with it, that resource is still available for everybody else to use. It's not part of a shadow IT infrastructure. And I didn't completely disrupt my larger system and how tightly designed it was. So it gives me the best of both worlds where I can go meet everybody's needs, be very flexible, and say yes as a central IT organization, but at the same time, kind of limiting the amount of shadow IT within the AI space that I have within these universities. And this kind of drives into this, this slide kind of really breaks down all of these different types of devices, right? When you think about, well, hey, everybody wants to talk about an NVIDIA A100. It's a great GPU, but it's not the only one, right? And so if I design my whole system around just an NVIDIA A100, right, what happens when I want to do FP16 workloads? Well, I've probably got too much of a GPU, right? Or FP32 workloads. There's other options that are better for that. Right? What happens if an FPGA could be better for certain types of jobs? Computational storage is growing. I want to be better at labeling. I want more storage. I want local storage in some jobs where I don't have them in all of them. Maybe I want to use a different network type. So many different possibilities that your schools of business will ultimately have or request. If I make a static, homogeneous style environment, I'm going to be saying no a lot. And composability has really enabled these universities to say yes a whole lot more. So here's kind of another quick example of during this use case where the benefit of composability has really kind of shined. And this goes beyond just that ability to go compose and give unique resources, but it also actually, as these resources got larger and they started wanting more of these resources in a single node, the performance has actually increased. So you'll see here on the left, you're going to see a standard converged server, meaning I have 8 GPUs living inside of it. I'm running a workload on those 8 GPUs. And on the right side, we actually compose those same 8 GPUs to that single node. And you're going to say, hey, those 8 GPUs that are composed, they've got to be slower, right? They live in a resource box, they connect over a network. They're not plugged directly into the motherboard of the server. Of course, those 8 converged GPUs have to be faster, right? So it drives into the next slide, the performance slide. You look at when I used a workload with 1 GPU. They're pretty much on par. In fact, if you look real close, you'll see that the converge is slightly faster than the composed. Then you get to 2. Then with 4, you start to see even a slightly bigger difference, right? This is where having those GPUs on that motherboard as close as possible to each other and as close as possible to the server and the data has had a slight impact in performance. Now we drive to 8. Right now, unless you can see this huge jump between what was composed versus converged. And the reason why is when we go back to that last slide, you'll see that the servers on the left have 8 GPUs, but 4 are assigned to one CPU, 4 are assigned to the other CPU. In the composed model, all 8 of them are assigned to the same CPU. And if I wanted to assign more than 8, they can still be assigned to the same CPU. And the value here is when those GPUs are intercommunicating to each other, they're all talking in their ring or in their mesh network, right? You're not crossing the UPI or QPI. Everything is talking directly to each other, and they're all staying within their own PCIe fabric. By having everything separated by those 2 CPU links, it significantly slows that process down. So we've partnered with SDSC and Bright Cluster Manager. Together with Gigaio, we made a very powerful system that we're going to be using to go support a lot of different universities. And some of the big values in putting this solution together was having this super easy to use platform that's designed to meet many, many different needs. So we're not setting up to solve one problem, we're set up to solve many different types of problems and doing it very efficiently so that I don't have wasted resources sitting isolated into a box. We're able to really allow that cloud-like agility. So today, one of the challenges that a lot of customers have is when they don't have that right resource, they're going to try to burst to the cloud. Well, by composing all those resources, we really gave that cloud-like functionality. And then when you merge it together with Bright Cluster Manager, you've made it so that it can be seamless, where the end customer doesn't even know that it's there. They just simply ask for certain resources because that's what their software would like, and it goes behind the scenes and it builds exactly what they need. So we're getting optimal resources at exactly the right time. And that drives in, again, faster time to results. And then, of course, again, the procurement flexibility. So thank you all for your time. I really appreciate it. This is, again, Matt Demas, CTO Field Sales at GigaIO. And I'd like to thank Frank and Martijn for their time as well.